Graph Theory Class 3 Video 2. In this video we're going to talk about walks, trails and circuits. Let's begin. The definition. So a walk on a graph is an alternating sequence of vertices and edges so that each edge only follows and precedes a vertex to which it is connected. So that's a really confusing way of saying something which is geometrically really simple. A walk on a graph is you just start at a vertex and you trace out a path, a walk, where you can only travel along edges to neighboring vertices. Okay, so you have to travel along the edges from one vertex to another vertex, and you're not allowed to jump, and you're not allowed to make new edges or anything like that. A walk on a graph is just you following the edges. Okay, a trail is a special type of walk. It's a walk with no repeated edges. Okay. And finally, a circuit is a trail that begins and ends at the same vertex. So another way of saying that is a circuit is a walk which begins and ends at the same vertex and it doesn't have any repeated edges. Okay, so these are the three definitions I want to talk about. So let's do an example. Okay, so here's a graph. It's a bit of a confusing graph. I've labeled the vertices and the edges. Okay, and I just want to describe a walk. So one possible walk could just be A, B, B, C. And geometrically, what is this? You start at A, you follow lowercase a, that takes you to uppercase B. You follow lowercase b, that takes you to uppercase C. So this is a walk and it's a trail. Okay. Notice that to describe a walk, you have to make sure you're being unambiguous, and it's not sufficient to just say ABC. Okay. This is not sufficient because it's ambiguous, because I start at A, I go to B, but there is actually two different ways of getting from B to C, right? So you can't just say A, B, C. You need to specify what edges do you take. Okay, so this is not sufficient in this case. Let's do an example of a circuit. So maybe B, C, C, E, D, F, B. Okay, so if I was to draw this, I start at B, I do C, down to C, I do E, across to D, and then I do F back up to B. So I end where I started and there's no repeated edges. So that means that this here is a circuit. And every circuit is also a trail, and every trail is a walk. So it's all three of the things. Okay. Maybe I'll do something which isn't a trail. So I could do B, F, D, E, C, D, D, F, B. It's a bit fast, but once you start thinking about it geometrically, it's quite simple. So that's B, F to D, E to C, D, back to D, and then F back to B. So it's got the edge F twice. It's got a repeated edge, which means it's a walk, but not a trail and not a circuit, because it has a repeated edge. Okay, so I just want to do one more quick example, and this example is just to show you sometimes you can get away without labeling the edges. So in this graph here, you notice that it's not a multigraph. There are no multiple edges between any two pairs of vertices. So that means writing something like ABC is actually unambiguous. It's okay to write ABC now, because there's only one possible way of doing this, right? There's no multi-edges, so writing ABC a well-defined way of describing a walk, which is also a trail. Okay, so if it's a graph without multiple edges, you don't actually need to include the edge labels when you're describing walks. If it has multiple edges, you definitely do need to include the edge labels. Okay, the thing to keep in mind is, think about your reader, think about the person who's going to be reading your work, and make sure that it's unambiguous what you mean. Make sure that what you write can't be misinterpreted, or that it's not well defined. Okay, let's move on to another definition. So this definition is very important. Okay, it's very, very important, and it's going to come up again and again and again over the next few lectures. So what does it say? This definition says an Eulerian trail is just a trail that uses every edge. Okay, an Eulerian circuit is a circuit that uses every edge. So the word Eulerian is just a modifier, which means use every edge. Okay, and also I want to point out the word Eulerian comes from Euler, the person who solved the bridges of Königsberg problem. Okay, so he got this named after him. And the last part of this definition is an Eulerian graph is a graph with an Eulerian circuit. Okay, this bit, the last part, is perhaps a part where people forget this definition. Eulerian graph means Eulerian circuit. So a graph is Eulerian if it has an Eulerian circuit. And not every graph has an Eulerian circuit. There are some graphs that just don't, as we'll see soon. So let's do a quick example. Here's some graph, right? And the question is, does it have an Eulerian trail? Does it have an Eulerian trail? Well, let's just try, okay? I'm going to start at C for no particular reason, and I'm going to try and hit every single edge once. But I missed that middle edge, so that doesn't work. Okay, maybe I'll start at E, and I just want to try and hit every edge once without repeating. Well, now I've missed this edge here, so that doesn't work. Okay, maybe this is one of those examples where it's sort of fun if you pause the video and try it yourself. Okay, but I'm going to tell you the answer now. So if I start at A, I think I can probably do this like that. Okay, and if I was to write out what I just did, I would say that's A, E, D, C, B, A, D. Okay, A, E, D, C, B, A, D. I hit every edge exactly once, and I never repeated an edge. I mean, I repeated a vertex, but that's okay. Eulerian has nothing to do with repeating vertices, it just cares about repeating edges. So does it have an Eulerian trail? Yes. Here's one right here. Okay, it's not the only one. There are more than one Eulerian trail in this graph. Okay. Well, how about another question? Does it have an Eulerian circuit? Is it possible to use every edge and return to where you started? Okay. Well, this is a much harder question. Okay, whether this graph has an Eulerian circuit, and you can try it yourself. You know, try and find one, or try and convince yourself that there isn't one. But I'm not actually going to tell you the answer in this video. You're going to have to try and work it out for yourself. That's the end of this video.